For gases, measurements of pressure, volume, temperature, and moles are all interrelated to each other. There are several gas laws that help us define these relationships, and in this PowerPoint, we'll cover the basic gas laws and how they combine into the two that you will use most frequently, the ideal gas law and the combined gas law. The first gas law we'll look at is called Gay-Lussac or Amundsen's law. Imagine a gas inside a sealed fixed-shape container. It has a certain pressure associated with the force of the gas particles colliding with the surface of the container. Now imagine heating that container. As you increase the temperature, the pressure of the gas inside the container increases as well. Those gas particles start moving faster with higher temperatures, and they hit the walls of the container with greater force. This is Gay-Lussac or Amundsen's law, that the pressure of that gas in the sealed container is directly proportional to its temperature. So we can also look at this relationship mathematically. The data set here represents measurements of temperature and pressure for a gas inside a sealed fixed volume container. And we can see that as temperature of that gas increases, so does the pressure. And we can graph this data. If we plot it on a graph of temperature versus pressure, we'll see that it's actually a straight line or linear relationship between temperature and pressure. And that means that we can write an equation for this line where pressure is equal to a constant value, here labeled K, which represents our slope, times our temperature in units of Kelvin. All gas laws use temperature in units of Kelvin. And we can see in this relationship that as temperature increases, so does pressure. Another way of writing this mathematical equation that's often used for Gay-Lussac's law is that pressure divided by temperature for a gas in a sealed fixed volume container will always equal a constant value, in this case K. And again, you can see even in this form that as temperature goes up, so does pressure in order to maintain K as a constant value. The second simple gas law is Charles's law, and it states that the volume of a fixed amount of gas kept at constant pressure is directly proportional to its temperature. Notice the difference with Gay-Lussac's law. In Gay-Lussac's law, it was pressure that was directly proportional to temperature as long as volume was kept constant. In Charles's law, volume is proportional to temperature, while pressure is kept constant. So imagine filling a hot air balloon. In order to expand the gas inside the balloon, the air is heated. As the gas molecules are heated, they move farther apart and the balloon expands. Since the molecules are farther apart, the gas inside the balloon is now less dense than the air around it, and the balloon rises. So we can also examine this relationship mathematically. This data set is for a sealed gas, a fixed amount, at a constant pressure. And what we see here, when we keep everything except temperature and volume constant, is that as temperature increases, in this case from 111 to 270 Kelvin, so does volume. And we can graph this relationship again, and we'll find that it is a linear relationship between volume and temperature. And that leads us to a mathematical formula for Charles's law, that is volume equals a constant value K, which represents the slope of the line, times temperature. And so as temperature increases, so must volume. And another common way of representing this is, again, volume divided by temperature for a gas of fixed amount and fixed pressure will always equal the constant value K. The third simple gas law is known as Boyle's law, and it states that when temperature and amount of gas are kept constant, the pressure of the gas is inversely proportional to the volume. So imagine gas inside a sealed, airtight syringe. If we push in the plunger on the syringe, it will decrease the volume of the gas. If we were also able to measure the pressure of the gas at the same time, we'd see that the pressure increases as that volume decreases. This is an inverse relationship. As one variable decreases, the other increases. And graphically, inverse relationships look like this, a parabola. We can actually transform this into a linear relationship, though, if we graph the inverse of pressure instead of straight pressure. So 1 over P instead. And then we would get a straight line that we could write an equation of that line. And it would look like this. The inverse of pressure, 1 over P, equals the constant K, which represents the slope of the line, times volume. And we could actually rearrange this so that pressure and volume are on the same side. In order to do this, we'd actually have to multiply both sides by pressure. It would cancel out on the left-hand side, and I would get pressure times volume on the right-hand side. I could then divide both sides by the constant K, and I would find that pressure times volume equals 1 over K. And since K is still a constant, it's the slope, that means 1 over K is also a constant. So pressure times volume equals a constant value. This is the heart of an inverse relationship. If pressure increases, then the volume has to decrease so that 1 over K remains the same constant value. The last simple gas law is known as Avogadro's law. It states simply that when pressure and temperature are held constant, the volume of a gas is directly proportional to the number of moles of a gas present. So imagine blowing a bubble with bubble gum. You inflate the bubble or increase its volume by blowing air into it, and that increases the number of gas molecules in the bubble. Mathematically, this is a direct relationship, so it can be represented by the equation volume equals a constant, in this case K, multiplied by the number of moles for that gas. And we can rearrange this, of course, just as we did the other gas laws, so that volume divided by moles equals the constant value K. Now, all of these simple gas laws allow us to relate one variable to another, assuming we're able to keep the other factors constant. The ideal gas law combines all of these different simple gas laws and allows us to solve for any combination of pressure, volume, temperature, or moles of gas. So this is the equation associated with the ideal gas law. Pressure times volume over moles over temperature equals a constant value R. And R stands for the ideal gas constant. And for any gas, that value is 0.08206 atmospheres times liters divided by moles divided by Kelvin. The units on the ideal gas constant simply represent the units that we use for all the other measurements in the equation. Pressure is always used in units of atmosphere. Volume is in liters. Moles is moles. And temperature is always used in units of Kelvin. So we can multiply both sides of this equation by moles and temperature in order to get rid of our denominator, our fraction. And what we would get is the second form of the ideal gas law, PV equals nRT. So let's look at an example calculation using the ideal gas law. How many moles of gas are in a basketball with a total pressure of 24.3 psi and volume of 3.24 liters at 25 degrees Celsius? So we're given pressure, volume, and temperature, and we're asked to solve for moles. These are all the variables you will find in the ideal gas law. And we can rearrange this form of the ideal gas law so that moles are by itself by dividing both sides by R and T, and we get moles, or N, equals PV divided by RT. So we do need the ideal gas constant, of course. That's 0.08206 atmospheres times liters divided by moles in Kelvin. And we just need to make sure that all of our other variables are in the right units to cancel out. So pressure needs to be in units of atmospheres. So we can convert into atmospheres using the conversion factor given here. And we'll set it up so that PSI cancels out. So the 14.7 has to go on the bottom. We get 24.3 times 1 divided by 14.7. That gives us 1.653 atmospheres. I'll carry one more significant figure than I really need. And I'll round at the very end of the calculation. Our volume is in units of liters, which is the appropriate unit for volume. For temperature, we do need to convert into Kelvin, so we add 273.15 to our Celsius temperature, and we get 298.15 Kelvin. Now we can substitute all these values into our equation, and notice what happens to the units. Our atmospheres will cancel out, our liters will cancel out, and our kelvins will cancel out. We're going to be left with moles. We're actually left with 1 over moles, but the 1 over a fraction is simply the same as the reversed fraction. So 1 over moles would become moles, our final unit for N. We do the math, 1.653 times 3.24 divided by 0.08206 and divided by 298.15, and we get 0.2189 moles, which we round to 3 significant figures to match the least number of significant figures in our problem, which corresponds to both our pressure and volume measurements. So a variation on this is called the combined gas law. And this is one that we use when moles of the gas are held constant, and we look at how pressure, volume, and temperature change relative to each other. So the formula is actually P1V1 divided by T1 equals P2V2 divided by T2, where P1, V1, and T1 represent initial conditions of pressure, volume, and temperature. Something happens to change those conditions, and we represent the new conditions, or the final conditions, as P2, V2, and T2. So let's look at an example of a problem that requires the use of the combined gas law. If you take a basketball at normal conditions, 24.3 psi, 3.24 liters, and 25 degrees Celsius, to the bottom of the Mariana Trench, the deepest part of the ocean, what would the new volume be? The pressure and temperature at the bottom of the trench are approximately 16,000 psi and 4 degrees Celsius. So in this problem, we're given pressure, 24.3 psi, volume, 3.24 liters, and temperature, 25 degrees Celsius, at one set of conditions. So we'll label these P1, V1, and T1. And then we're asked what the new volume would be at a different pressure and temperature conditions, so 16,000 psi and 4 degrees Celsius. So two sets of pressure, volume, and temperatures means the combined gas law. Now, we don't have the ideal gas constant in this particular law, so our units, particularly for pressure, are not as critical. As long as we have the same units for P1 and P2, and actually the same units for V1 and V2, we don't have to convert those into something else. The only unit that we really have to be concerned about is temperature. Temperature always must be in Kelvin to use the gas laws. So we do have to add 273.15 to both of these temperature values, and that's what we'll put into our denominators. So we substitute in what we have, and we want to solve for V2. So I would start by actually simplifying what I have written here. So I'd actually do everything on the left-hand side, put those together, 24.3 times 3.24 divided by 298.15. And on the right-hand side, I'd take 16,000 and divide it by 277.15. And this is what you would get. We can then isolate V2 by dividing both sides by 57.73. And notice what happens to the units. Our units of pressure and our units of temperature in Kelvin actually cancel out. And we're going to be left with units of liters for our volume. And so it gives us 0.00457 liters. We can round this to two significant figures, which is the same as our least number of significant figures in our problem. And that's actually 4.6 milliliters. So the basketball shrinks from 3.24 liters to 4.6 milliliters at the bottom of the ocean. In summary, the ideal gas law allows us to determine amount of gas for any combination of pressure, temperature, and volume. And the combined gas law allows us to determine changes in pressure, temperature, and volume when moles of gas are kept constant. Both of these laws are combinations of the simpler gas laws.